car of mass 1500 kg is pulling a trailer of mass 750 kg up a straight hill of length 800 meters inclined at an angle of sine inverse 0.08 to the horizontal. The resistances to the motion of the car and the trailer are 400 newtons and 200 newtons respectively. The car and trailer are connected by a light rigid tow bar. The car and trailer have speed 30 meters per second at the bottom of the hill and 20 meters per second at the top of the hill. So for part A, we have to use an energy method to find the constant driving force as the car and trailer travel up the hill. The energy method, a very simple formula that you can always use, is that the total work done by the driving force is always equals to the change in kinetic energy plus the change in potential energy plus the work done against friction. So for this equation, I will be looking at the entire system, meaning the car and the trailer together rather than individually. So for the total work done by the driving force, we know that the car is pulling the trailer up a hill. So the engine of the car is exerting a certain driving force which is unknown. So the total work done also has a formula of driving force multiplied by the distance traveled, and in that case that is the length of the hill, which is 800 meters. That will be 800. And then we have the change in kinetic energy, which has a formula of half times m multiplied by the squared minus initial velocity squared. And then the change in potential energy is always the mass multiplied by gravity multiplied by the change in height. Work done against friction, that is the force of friction multiplied by the distance traveled. When I say that I will be looking at this entire system for this equation, what that means is that when we're talking about the energies, I will look at the energy that both the car and trailer exert together. So for example, when we're talking about the mass, we will talk about the mass of the car and the trailer. So that will be 750 plus 1500, so that's 2250. And then when we're talking about the force of friction, we will be taking both the friction of both the car and the trailer, so that is 400 and 200, so that will be 600. Driving force multiplied by 800 is equals to half times 2250. And then they've given us the final speed, which was 20 meters per second at the top of the hill, so that will be 20 squared. And then the initial speed was 30, so that will be 30 squared. Potential energy and the work done against friction, I will be doing the workings over here. So for the change in potential energy, we have mgh. So for m, we will be using 2250. And then the force of gravity is 10. Now, in order to find the change in height, we'll have to look at the hill as a right triangle. The hill's length is 800 meters, so that means this hypotenuse will be 800 meters. And they also told us that it is inclined at an angle of sine inverse 0.8. So this angle is sine inverse 0.8. And then this perpendicular will be the change in height. Since it is going from the bottom of the hill, so this is height 1 and then this is height 2. So this perpendicular will be the change in height. So we can use a trigonometric identity in this, so which is sine theta. So theta in this case will be the angle of the hill. Sine, and then for the angle, we know that they've given us the angle as sine inverse 0.8. That means sine of sine inverse 0.08 must be equals to perpendicular, which is the change in height, over the hypotenuse, which is 800, the length of the hill. Now sine of sine inverse just leaves 0.08, so that means that 0.08 must be equal to the change in height over 800. That makes that change in height equals to 800 multiplied by 0.08, which is equals to 64. So that is the change in height, which we can take back into the change in potential energy formula. 2250 times 10 multiplied by 64. That makes the change in potential energy equals to 1440000. And as for the work done against friction, we have the force of friction on both the car and the trailer, 600, multiplied by the distance traveled, which is 800, and that will be equals to 480,000. Now we can use these values in the initial equation which we were writing. To simplify that, again we get the driving force multiplied by 800 is 144, and then plus 480,000, which is the work done against friction, and that simplifies it down further, and 135,700. Then dividing 800 on both sides, we get the driving force equals to 1696.875, and if we want to round off, that is 1700 newtons. So that is the driving force exerted by the car. So for part B, they are saying that after reaching the top of the hill, the system consisting of the car and the trailer travels along a straight level road. The driving force of the car's engine is 2400 newtons and the resistances to motion are unchanged. So we need to find the acceleration of the system and the tension in the tow bar. So the new changes that they've given us, that instead of traveling on a inclined hill, now we have a straight level road. Other than that, now they've given us the driving force of the car's engine, which is essentially the driving force of the entire system since the car is pulling the trailer upwards. So that is 2400 newtons. And other than that, we have the resistances to motion, which are the same. So for the car it was 400 and for the trailer it was 200. So in order to find the acceleration and the tension in the tow bar, we will use the forces formula, which is forward force minus resistive force is equal to the mass multiplied by the acceleration. This is the best option since it includes both the acceleration and the tension in the tow bar. So now when we're using the forces formula, we will not look at the entire system, rather we will look at the objects individually. So for the car, the forward force is the driving force that it exerts. So that will be 2400, and then it will also have a force of friction, which was 400 acting on it, and other than that it will have the tension, and its mass was 1500, and then we have the acceleration. So both the car and the trailer will have the same tension and the same acceleration since they are connected through a tow bar. Since the trailer is behind the car, the tension in the tow bar will act as a driving force for the trailer and it helps it move forward. So for the trailer, the tension will be the forward force, and the resistive force will be the friction, which we established was 200, and then we have its mass and 750, the acceleration. Two are simultaneous equations, and since we have two like terms, the acceleration and the tension, we can cancel out this plus t and minus t. So this becomes 2400 minus 400, which is 2000, and then subtract it with the further 200, we get 1800, and then 1500 plus 750, we have 2250A. We get acceleration is equals to 0.8. Now substituting this acceleration in the first formula, the car's formula, we can find out the value of tension. So 2400 minus 400 will be 2000, and then minus t, which was the tension, is equals to 1500 times the acceleration, which is 0.8, and we simplify it further. So we get 2000 minus t is equals to 1200, which the tension in the tow bar is equals to 800 newtons. With that, we're done. since we have both the acceleration as well as the tension in the string.